Actually it is nothing but, its basic principle is nothing but balanced wisdom bridge. The principle of this meter bridge is nothing but balanced wisdom bridge. So we know balanced wisdom bridge means it has four resistors connected in the form of a quadrilateral, and when that ratio P by Q is equal to R by S, then no current flows through the galvanometer. Galvanometer indicates zero reading. So that means here also its experimental arrangement will be same here. So that means similar to that wisdom bridge. This is one resistance here, and this is another resistance, and this is a wire up to here A to J we consider as one resistance, and J to B we consider this as another resistance. So right, and so now here see this is nothing but our bridge wire we call here AB wire, so which is nothing but of exactly 1 meter length. So that is why we are calling this device as meter bridge here. This bridge wire here, this is nothing but we call the bridge wire here. So this is of exactly of length 1 meter. So now I will show you that experimental setup regarding this, how this experimental setup will be. In lab also you have a practical based on this. So let us see this experimental setup here. Experimental setup, how this meter bridge is. So let us see the first assembly of this meter bridge. So the components required for this circuit diagram here. This is unknown resistance galvanometer, and this is a resistance box. It has a 2 gaps here. This is a bridge wire. So this practically the device will be like this. So observe this device here. It is having this meter scale, and above this meter scale you can observe this. This is the wire here. What I said AB wire. This is nothing but that wire here, right? And then these are the metal strips. These are generally made up of the copper strips. This is copper in color. You can observe that. And so then this is another strip here. That means totally 3 copper strips. We can set them totally. This has 1 strip here, and this is another strip, and this is another strip here. So that means 3 copper strips are arranged. We are naming them as A, D, C. So that 3 copper strips are there here by leaving 2 gaps. So this is 1 gap. We are naming this as a left gap, and this is the right gap. So that means by forming the 2 gaps, then this experimental arrangement will be there. And so now this is our bridge wire here, and below this bridge wire a scale is fixed, a meter scale is fixed here, on which we can measure the balancing length. So we will discuss about that balancing length. So this, for that measuring that balancing length, we are fixing a meter scale here, right? So these are we connect this unknown resistance in one of the gap here. So generally here we are saying it as a left gap, and actually we interchange those unknown resistance here. So then once we connect, so here this first we are connecting this unknown resistance. This is unknown resistance wire here. It is connected in the left gap here. So the next the galvanometer is connected from this middle strip here. This is our galvanometer connection. That galvanometer connection start here. So one terminal of the galvanometer is connected here, and this is another terminal. This is a galvanometer here, which we discussed already. And then this another terminal is connected to the jockey. This is a positive terminal. This positive terminal is connected to this jockey here. So jockey is like our this is the arrangement of this jockey. So it can be kept in. We can make the contact at any point here on this wire. So there is a jockey arrangement. And resistance box is connected in this left gap here. Sorry, right gap. So here we are connecting this. In one gap, left gap, we connected the unknown resistance, and in the right gap we are connecting this resistance box. So this is the resistance box we discussed already. We can keep any desired resistance here. And then we connect the battery here. So then that means out of this bridge wire, one end is connected to the negative terminal and the other end is connected to the positive terminal. Suppose say this end is connected to this negative terminal of this battery through the key. So this is a one-way key here. When this plug is inserted, key is on, it is switch on. If it is removed, then it is off state. So then this one terminal is connected to this battery here, negative terminal of the battery. That key is connected to the one terminal of the battery here, and the other negative terminal is connected to this another end of this bridge wire here. So this is another end of this bridge wire. So that is the experimental connection here. Now we can observe this circuit here, experimental arrangement of this meter bridge. Got it? So that is the experimental procedure. And now let us see how to proceed for this. What is the procedure for this experimental procedure? Let us see this. Now see the experimental procedure for this galvanometer. So after giving the connections, as I said now, next we need to proceed for this experiment here. So let us see the experimental procedure for this galvanometer now, this meter bridge. So that means now here we take out this one of the plug here to check for the connections. First we need to check the connections whether they are correct or not. So we are removing this one of the resistance here. Suppose a 100 ohms we are removing, and now here this is we are closing the circuit here. So that means now here you can observe that. Now here you can observe this here. So I will show that again here. So that means now if you close this, if you put this plug here, then the circuit will be closed. Now you can observe this when it is taken out, a gap is there here. A small gap is there here. So now we can observe that clearly here. A small gap is there. So that circuit is open now. So if you put that plug there, then circuit will be closed there. That is the switch here. Generally switches means then it will be like this. In terms of the plug point will be there. So if you remove that plug, then circuit is switched off. If you close it, then that circuit is switched on, so that it will arrange the conducting path here. It will close that gap here. So that's, observe this, when you are closing this, then it will arrange a conducting path here. Now the path is closed, path is arranged here. So then after that we are switch on the circuit here. So then first here we need to check our connections, whether our connections are correct or not. So for that what we do is we press the jockey at both ends of the circuit here. Suppose if we are pressing at one end, of this meter bridge wire here, then observe the deflection in the galvanometer, and then we press the jockey at the other end of this bridge wire, and then we observe the deflections. If the deflections in this galvanometer are in opposite in directions, then our connections are correct. If the deflections are on the still one side of this 0, that means deflections are on the same side for both ends, then there will be some fault in that connections there. So we need to check that connections. There may be some loose contacts may be there, or some wire may not be connected properly. So we need to check those connections there. So after that, after checking and after concluding that the connections are correct, then we need to proceed for our experimental experiment now. So then for this proceeding experiment, our aim is to find the unknown resistance here, right? For finding this unknown resistance, then we arrange some known resistance in this right gap here. So that means as we discussed here, we need to place some known resistance in the right gap and unknown resistance in the left gap. And actually finally we interchange there. That is not a compulsory condition for us. So here as we arranged, as we discussed now, we are arranging some known resistance in this left right gap. So known resistance means where we remove this desired value here. 100 ohms or 200 ohms or 500 ohms, you can remove our desired value here, so that some null deflection is obtained in that galvanometer. So then after that, so after removing that, we press the jockey at the different points here. So we press the jockey at different points until this galvanometer shows the 0 reading. The galvanometer should be at 0 reading. Then that is nothing but our balanced wisdom bits principle here. So we are pressing the jockey at different points until you will get the 0 deflection there. So when you are getting that 0 deflection, then that point is nothing but we call the balancing point there. So now we can observe that this galvanometer indicates 0 for this point, for example. Now this length is nothing but we call this balancing length here. And then we note this balancing length like this. So observe this. We note the balancing length from the end where the positive terminal of battery is connected. So that we consider as L. So now this AB length. So here in this experiment we are taking this AB length as L, and then this BC length we consider this as 100 minus L, because this total length is 100 centimeters, 1 meter or 100 centimeters. So observe that this the positive terminal is connected to the point A. So from that we are measuring this length here. So that we are taking it as L, and then this length, remaining length will be 100 minus L here. So then that remaining length will be 100 minus L. So then we note these values here. So by noting these values here in the laboratory, in case if you are doing that experiment, we repeat the experiment and then we find the balancing length here. Just for finding the balancing length, this is experimental procedure. So again say this, I will explain in terms of the circuit here. As you know already this, as you saw this already circuit. So this is the resistance box placed here. And so this is a resistance box where we are connecting the known resistance. Resistance box means we can put any desired value in that gap. And this is the unknown resistance here. So that means we connect the wire of which we are finding the resistance of which wire we need, that wire we connect here. And then this galvanometer is connected from this midpoint here, midpoint of this these two gaps. That one connection point will be there as I shown. So then from that we connect the galvanometer, and in general whenever you are taking this galvanometer, high resistance box will be there. In that here I am not showing that high resistance box. Whenever you are doing that experiment, high resistance box will be connected in series with that. That's a compulsory procedure, experimental procedure. So I am not showing here. When you are approaching the zero, then we remove that high resistance box, or we short circuit that high resistance box there, right? So this is a jockey. This jockey is nothing but, as I shown, it is like our pen, or I can say exactly it is like our highlighter. Color highlighter will be there. So it exactly like that. A back wire will be connected so that we can press it at any desired point here, and we observe the deflections at each point in that galvanometer. And so our procedure is, first we press at the both ends. Once we press here and once we press here. Then the deflections in the galvanometer should be opposite in direction, right? And so then the deflections are in opposite direction means our connections are correct. If the deflections are by mistake, if the deflections are in same directions, our connections are wrong, or there may be some loose contacts may be there. So as I said, connections here means we are turning, we are giving the connections in by rotating the just a screw here. So there may be some loose contacts may be there. So we need to check all the connections again whenever you are getting some deflections in the same directions. So after that we press the jockey at different points on this wire here, bridge wire, until you will get zero reading here, right? Until you will get the zero deflection in the galvanometer. Once you are getting the zero deflection, so that point is nothing but we are calling it as balancing point. Suppose here we are taking this B is a balancing point here, so that AB length is nothing but we are calling as balancing length, and BC length is nothing but we are calling, and that means that is taken as 100 minus L here, L1, L2, or you can take L and 100 minus L centimeters you can consider. And actually while doing that experiment, the resistance, that means it is not the compulsory condition like resistance is connected in the left gap. So actually while doing that experiment, first we take the reading by connecting this in the left gap, and then we interchange this resistance here, but for getting the average values to reduce the errors. So that means next we connect the resistance box in the left gap, resistance box in the left gap, and then unknown resistance in the right gap, and again we repeat the procedure there, and so that we will get this balancing length here. That means again balancing length you will get. From that we calculate the unknown resistance, and finally we find the average values there, right? So that means in experiment generally we repeat the experiment for these different values here, different values of this currents in that circuit, and different values of the resistance in that resistance box there. By changing the values in the resistance box, we repeat the experiment, and for each value we find the unknown resistance, and finally we find the average values there, right? That is the experimental procedure here. Now see the mathematical equations related to this. And so now here this is our circuit here as we discussed now. So here I am taking, generally we are taking that balancing length point, we take it as J here. I previously explained it as some B. So here AB I am taking as a bridge wire here. Generally in most of the cases we consider that as AB as a bridge wire. It is no problem here whether you are taking B or C. So then AB is our bridge wire here, and so then C, and this J is the point where this jockey shows the zero reading. That means jockey is pressed here so that the galvanometer indicates zero reading. So this length is L centimeter, and the remaining length will be JB will be 100 minus L centimeters. Now this is our Wheatstone bridge here. You can observe this. This is nothing but 4 resistors. You can consider this as P, Q, R, S. So then if you are writing this, when galvanometer shows zero reading, it is already indicates that the bridge is a balanced bridge. So then P by Q is equal to R by S we can write. So that we are writing this R by X is equal to, this is P and this is Q. So R by X is equal to, P by Q is equal to is nothing but R by X, that is equal to, here R by S we need to write. R is nothing but resistance of this AJ wire, and S is nothing but resistance of this JB wire. So then RAG by R JB we are writing. So then that we can write this as RAB by R by x is equal to AJ by JB. So why we are writing AJ by AB means you know that resistance is directly proportional to the length here. So resistance is directly proportional to length. Actually we can write this resistance as rho L by A. So here we are taking the wire of uniform cross section here. As we are taking the wire of uniform cross section and it is the same wire, this rho is constant and A is also constant. So we can write this R is directly proportional to L here. So that we are taking this L. So we are taking this as L here. That balancing instead of this resistance we are taking it as L. And so that we are writing this as AJ means it is nothing but L and this JB means it is nothing but 100 minus L. So that we write this R by X is equal to L by 100 minus L. And from that X value we can write here. That X value we can write this as R into 100 minus L by L. So that means whether it is R into 100 minus L by L or L by 100 minus L, that depends on whether you are connecting the resistance, unknown resistance in the left gap or unknown resistance in the right gap. So this expression we are writing this by connecting the unknown resistance in this right gap here, right? So that by connecting this unknown resistance in the right gap, we are writing this expression. If it is given that, if it is in the problem, if it is given like it is connected in the left gap means, then we need to change this formula here. That depends on whether it is connected in the right gap or left gap. But generally L means we consider this balancing length means we measure this from end where the positive terminal of this battery is connected here. You can observe this positive terminal is connected here, right? So this length we measure this as L, balancing length. So sometimes they may give it as balancing length. So balancing length means you need to take this value here, right? And next here there will be some errors will be there, and so let us see what are the possible errors and how to remove them. So the resistance of these copper strips fitted at the ends of the wire and that of the slider have not been taken into account. This is called end resistance. These are determined by the another experiment in terms of the length of the wire and are to be added to the two parts of this AB and basic. So that means here in this experiment, as we discussed, these are made up of this copper strips here, right? So when you are writing this balance and condition for the Wheatstone bridge, we are writing only these resistance here. So like this resistance R by X is equal to, then these values we are writing here, L by 100 minus L. That means only we are taking here resistance, and we are taking from A to J and J to B. But we are not counting this resistance here. Resistance of these copper wires we are not counting that. So that means that also to be, if you want to include that resistance also, then those are said to be end corrections. Those resistance are said to be end corrections. And so the resistance of these metal strips or copper strips will be determined in another experiment, and those are directly given in terms of the length, the equivalent length they will give here. So that is nothing but we are calling it as end resistance. These are determined in another experiment in terms of the length, and so now those lengths are to be added here. So now previously, for example, if I am writing like if X is connected in this left gap and R is connected in this right gap here, so suppose I am taking like this. If this is our experimental arrangement here, right? And so this Galvanometer connection and a jockey connection will be there like this. And so then this is AJB. This is L and this is 100 minus L we are taking here. And so now suppose if you are writing like X by L is equal to, let us take this as L1, this length as L1 and this length as L2 I am taking here. So X by R is equal to, now here this is the positive terminal is connected here. That's why I am assuming like this. Positive terminal is connected here, so that balancing length is measured from this. So then I can write this as L1 by L2, right? This is nothing but our previously what we discussed here. And so now this, if end corrections are also included, that means they will give in some problems, they will give that end corrections here. One of the previous IIT question is also there, we will discuss it later. So by giving this end corrections, they will ask the unknown value. Now if suppose this end corrections for this is given as some L1 dash for this left side, and for this right side it is given as L2 dash. Here I mentioned already, it is mentioned in terms of this length of the wire here, equivalent length of the wire they will give. So then just we need to write this as L1 plus L1 dash we need to write here. By L2 plus L2 dash we need to write here, right? This L1 is L only, you can take it as L, and L2 means 100 minus L you can cancel here. They will give some balancing length, that means end corrections in terms of the length. For example, this value is given as 2 centimeters for example, and this value is given as 1 centimeter. Then what I am saying is we need to write this as L1 plus 2 and L2 plus 1. So just simply we need to cancel like this. So whatever the lengths they are giving, so if they are giving L2 centimeters for this left side here, then we need to add that length to this L. And if it is given for this right side, then we need to add that length to this L2 here. Simply that you need to remember here. So that is a change you need to remember if the end corrections are given. So if end corrections are given, so this is the formula we need to use here. So that means that L1 dash is the end correction on the left side and L2 dash is the end correction on the right side. Got it? So those are the end corrections now. And next here, if the end of the meter if the end of the meter bridge is not exactly at the zero of the meter scale, or the knife edge of the sliding jockey and its index point are not in the line, right? And so now then the length of the wire, two parts AB and BC, read it as like here AB and AC means like we are taking this experiment as AJ and JB. This is, or BJ. A read on the scale will be different than the real length. So to remove this error, experiment is repeated after interchanging the unknown resistance and the resistance box. By doing this, error due to the non-uniform thickness of the bridge wire is also removed, right? So now let us come back to this experiment here. So here what will happen is this zero of this scale is not exactly here. That means here if suppose this 0 should be here, the 0 of the scale should be here and 100 centimeter should be here, right? And sometimes the scale may be because of wear and tear of the scale, the 0 of the scale may not coincide here. Suppose directly that 1 centimeter of the square is teared off, and so that here this only 1 centimeter directly starts here instead of this 0, right? If only 1 centimeter of the scale is there at that point, but we are thinking that as a 0 only. Suppose if this balancing length is some 40 centimeters, it is showing here. The balancing length is shown as 40 centimeter. Then actual balancing length will be that 1 centimeter less we need to consider here, because instead of 0, 1 centimeter is coincide with the point A here. So the actual balancing length will be 39 centimeters only you will get. So sometimes you will get such a type of errors here. So to eliminate those errors, what we will do is we interchange these two values. As I said, the resistance is not only connected in the unknown resistance is not only connected in the left gap or not only connected in the right gap. While doing the experiment, first we do the experiment by connecting it in the left gap, and then it is shifted to the unknown resistance is shifted to the right gap, and the resistance box known resistance is connected to the left gap. So by interchanging them, we find the average value so that these errors will be reduced here. So another possibility is the wire may not be of uniform cross section. So here actually it should be uniform cross section according to our calculation here. That means here we are writing this assumption, means we are assuming that as a uniform cross section. Suppose if the wire is not of uniform cross section, because of that also some error will be occurred in the calculation of the unknown resistance there. So if we interchange these two values and if we are finding the average value, then automatically that error is also reduced here. That error is also minimized. So we can minimize such errors just by this interchanging these two values here, interchanging those two resistance, known and unknown resistance values there. And another possible error is resistance are taken in the resistance box so chosen that null point is nearly in the middle of the wire, then percentage error will be less. In addition to it, the effect of end resistance will also be minimized. There is one more advantage. When the null point is in the middle, the sensitivity of the bridge is maximum, because then all the 4 resistors of this bridge are equal, nearly equal. So this we discussed here at the Wheatstone bridge itself. So in the Wheatstone bridge, when all the resistors PQ are all equal, then bridge is said to be more sensitive. So that for the small difference in that value also, you will get the exactly can find those small differences in that values also. That means unknown resistance also we can find more accurately. And so that means here we should choose that R value, the resistance in this resistance box, such that the null point, that means the null point or the neutral point should be, that means that the balancing length should be obtained at the middle of this scale, middle of the scale means nearly at 50 centimeters you should obtain. Then accuracy of the sensitivity of the device will be more, and so accuracy of this device will be more. The current should be allowed only. So next see this, the current should be allowed only for the current should not be allowed to flow in the wire for the long time, otherwise the wire will become hot and the resistance of the wire will change here. So that means this is, we know the resistance of the wire changes with the temperature. So if you are allowing that current, suppose if you are taking the readings and after you are doing the calculations to find this X value here by allowing the current in the wire, current to the circuit, the resistance of the circuit will increase because of heat produced in that wire. And so that if you are taking the next reading, then you will get another value because X value, that the resistance of that wire is changing there, so that you will get the another value instead of this previous value here. So that errors you will get here, more errors you will get. Because of that reason, the current should be allowed in that circuit only when you are taking this measurements there. Actually, that bridge wire, as I said in the beginning of this effect of temperature on the resistance, that bridge wire is made up of some materials called constantan or manganese. Because for those materials having that alpha value will be very small. The alpha means temperature coefficient of the wire will be very small. So because of that, those bridge wires are made up of such a materials. Those are actually alloys. So manganese or constantan, such a alloys, wire made up of such alloys generally be used in these experiments here. Because their effect of temperature will be minimum on that, but not zero. You should note that. So because of that reason, so we should allow the current only when you are taking the readings. So see the next one. In the initial adjustment, shunt should be used with the galvanometer. Near the zero deflection, the position of the shunt should be removed. This also explained here. So initially we should include the high resistance in that galvanometer. And when you are approaching that zero deflection, you can remove that resistance there. High resistance we can remove there. So that shunt is nothing but we know a small resistance connected across. That is another way of protecting the device, right? So we can connect a small resistance across that. We can use either high resistance box in series with the galvanometer, or you can connect a small resistance across this. That means you can connect a small resistance like this. If you are connecting a small resistance like this, then more current will flow through this shunt resistance here. Only a small fraction of current flow through the galvanometer, right? So when this reading in the galvanometer is almost approaching that zero, you can remove that shunt. So that is another way of protecting that. You can use either high resistance box or you can do like this. So next one is the sliding jockey should not be rubbed on the wire, otherwise the thickness of the wire will not remain same at all places. That means in the jockey, I showed jockey already, it is having some sharp edge like our highlighter. Like suppose if you are dragging on this wire here, then the thickness of the wire will changes here. Thickness of the wire will changes so that the resistance of this thickness is non-uniform. When thickness is non-uniform, here you will get the difference here, because here we are assuming that thickness is same here, right? And so here because of that, we should press the jockey only where you are placing it. That means we should not be dragged like this. If you want to place here, we should place here. Next we should lift the jockey, and if you are placing here, you should place there. So but it should not be dragged from here to here. So jockey should not be dragged along the bridge wire, so that we can maintain the uniform thickness of this wire here. So those are the precautions or the errors generally occurs in this meter bridge operators there, right? And so now let us see some problems on that. So that is the experimental procedure and experimental setup of this meter bridge. So as I said, in laboratory also it is there for you. So when you are coming back to the college, you have to do this experiment also in the laboratory, right? I hope all of you understood this. So that means this is the setup here, known resistance and unknown resistance here. This is the major thing you need to remember here. Balancing length means it should be measured from the end where this battery, positive terminal of the battery is connected there. So as I said here we are getting like x by r is equal to 100 minus L by 100. If for example, if I am taking this x is connected here, the resistance, unknown resistance is connected here, and resistance box is connected here, then you need to write the same formula as x by r is equal to L by 100 minus L you need to write here, right? So that formula will changes depending on that where you are taking this known resistance and where you are connecting this unknown resistance here. So that means that this is the case. This formula is used when unknown resistance is in the left gap, and when it is on the right gap, we use this expression here to find that, right? And so now let us see some problems based on this meter bridge here. And so now let us see this problem here. So bridge wire setup is shown is used to determine the unknown resistance X using a standard 10 ohm resistance. The galvanometer shows the null deflection when the tapping key is at the 52 centimeters. The end corrections are 1 centimeter and 2 centimeters respectively for the ends A and B. Then determine the value of X. So that is nothing but our end correction. That means I said this is a previous advanced question. This is a previous advanced question actually. So that is nothing but if end corrections are given. So we discussed already when end corrections are given how to write. Our general formula here is, suppose here I am taking this as L1 and this is L2 I am taking here. Then our general formula what we can write here is X by R is equal to L1 by L2 we need to write here. If suppose end corrections are given, the same expression we need to write this as, now observe this positive terminal is connected here. Positive terminal is connected and this X is in this left gap here. So that X by R is equal to L by 100 minus L we need to write here. And so that then this value we can write this as L1 plus L1 dash. This L1 dash is the error. End correction. L2 plus L2 dash we need to write here. So now this is our formula as we discussed already. So now just we need to substitute those values here. So this is X by 10 is equal to L is balancing length is given as 52 centimeters here. So this is a 52 centimeters here. So then 52 plus the end correction from the end for the end A is 1 centimeter. So this is the end correction for the end A. So plus 1 by this 52 means then remaining length L2 will be 100 minus 52. 100 minus 52 is nothing but 48 we can write. So this is 48 plus L2 dash is 2 centimeters. So plus 2. So therefore I can write that value as X by 100 is equal to 53 by 50 you will get. And therefore this X is equal to 53 by 5 you can write here by cancelling this 0. So then this is nothing but we can write this as 10.30 means we can write it as 0.6. 30 by 3 by 5 means so it is 10.5 ohm. Right, so that is our answer here, this 10.5 ohm. So that is when end corrections are given, so that is a way of solving that. So end correction for A should be added to L1 and end correction for this B should be added for this L2, right? And here based on this meter bridge only sometimes some unknown, that means some theoretical questions will be there like this. Suppose here two wires are connected like this in the left and right gaps for example. Now here I am taking this, this wire is made up of some semiconducting wire here. This is, let us say, semiconductor is connected here. This is like a general resistor only, like a conducting wire having some resistance is connected here. Now if suppose if the balancing length is obtained suppose say at L1, now if you are raising the temperature of the semiconducting wire, we are raising the temperature of the semiconducting wire. Then how this balancing length changes here, whether it increases or decreases. So then for that what we should identify is how the resistance X value changes with increase in temperature. If you are increasing the temperature, how the resistance X value changes here. So I said this is made up of semiconductor. So for semiconductors with increase in resistance, with increase in temperature, resistance of this wire decreases, right? So because it is made up of semiconducting material, so semiconductors are having this negative alpha value, negative temperature coefficients. Negative temperature coefficients means they are having this, that means if the temperature is increasing, the resistance value decreases. So when X value decreases, L1 value also decreases. Now we can observe this. You can observe this formula here, X by R is equal to L1 by L2. If X value is decreasing, then automatically this L1 also should decrease here. So then L1 value also decreases, and so that this balancing length shift to the right side, left side, that shift to the left side, balancing length is decreasing there, got it? So that is the case when semiconducting wire is connected here and if you are raising the temperature. For example, if instead of this, now I am taking this semiconducting wire is connected here. This is made up of semiconductor and this is like a conducting materials only having some resistance. Now again we are raising the temperature. Temperature of the system is increased here. Temperature of these two resistors are increased here. Then with increase in temperature, resistance of this wire will increase and resistance of this wire will decrease here. So as a result, here this resistance is decreasing and here this resistance is increasing here, right? So this resistance is increasing. So then here balancing length should increase here. So this balancing length should increase means this balancing point should shift to this side here. So balancing point shifts towards left. So that balancing length increases here. So such a type of theoretical questions they will ask. So write that as a note here. So write that as a note. So just mention that note here. When a semiconducting wire is connected in the left gap, when a semiconducting wire is connected in the left gap, and if its temperature is increased, and conducting wire is connected in the right gap, a conducting resistance is connected in the right gap, semiconducting wire is connected in the left gap, and a conducting resistor is connected in the right gap. If the temperature of semiconducting wire is increased, if the temperature of the conducting wire is increased, semiconducting wire is increased, then its resistance decreases, and so balancing point shift to the left, So if nothing information is given like whether it is battery is connected to the positive terminal is connected to the right gap or left gap, we consider this as a standard circuit here. So remember this, we consider this as a standard circuit. Standard circuit in the sense then batteries left gap and right gaps are like this. These are left and right gaps here. So battery is assumed to be connected to this end here. So that balancing length means we need to measure from this left end. So write this like this. So if nothing is given, if any other circuits are given, then according to the circuit we need to consider that, right? So remember this point here. So here what I mentioned is if semiconducting wire is connected here and if you are increasing the temperature, its the resistance decrease, and so that here balancing length also should decrease, so that this point will shift. The balancing point will shift to the left. And if it is reverse, then you can answer that. Like if a resistance is connected here, or mention that also. If a resistor made up of conducting materials is connected in the left gap, and if its temperature is increased, then its the resistance increases, and so balancing point shift to the right. Balancing point shifts to the right. So got it? If you are taking this as a resistor, then here with increasing this temperature, the resistance will increase, and so that here balancing length also should increase. So that means if you are increasing the resistance here, simply balancing length should increase. If you are decreasing the resistance, balancing length should decrease. So now let us see this one problem based on this direct application here. So that means here it is given as simple potentiometer. It is nothing but meter bridge only. So that means simply in the simple circuit let us consider here. So in the simple circuit where the length AB of the potentiometer wire, that is also meter bridge wire only. Meter bridge wire, the resistance X and Y have the values 2 ohms and 5 ohms and 2 ohms respectively. When X is shunted by a wire, the balancing length is found to be 0.625 meters from the A. What is the resistance of the shunt? If the shunt wire has a length 0.75 meters long and 0.25 mm in diameter. What is the resistivity of the material of the wire? So that means basing on this different problems will be there, simple problems will be there. I am not going to discuss all those formula based problems. You can solve those problems easily. So now here in this problem what they are giving is these two resistors are given here, and now we are connecting a shunt resistance across this. That means across this X we are connecting some another resistance here. We are connecting some another resistance here. Suppose let it be R, and then we are finding the balancing length here. So when you find the balancing length, it is obtained as 0.625 meters they are giving here from the end A. So that means that is the distance from this end here. Then what is the specific resistance of, what is the resistance of the wire, and then it's a specific resistance they are asking here. Got it? Now just we need to take that instead of this X by R, X by Y, we need to take this total resistance, effective resistance we need to consider here. Whenever two resistors are connected like series or parallel, so sometimes such a combinations will be there. Whenever such a, instead of this one resistance, if two or more combinations are connected, so we need to take our effective resistance here. So that effective resistance means we can write this as Rx by R plus X, since both are connected in this parallel, by Y. That means this total it is one resistance, X by R formula or X by Y is equal to, this balancing length is like 62.5 by this remaining length will be 37.5, right? So then you can simplify that. So X and Y values are given here. So then I am substituting that X and Y values here so that you will get these expressions like this. So that means now this is X is nothing but 5 and R is nothing but 2. That means Y is nothing but 2 ohms. So if you substitute and here simplify that, on simplifying you will get this Y is this unknown resistance R is equal to 10 ohms you will get, right? And then in addition to this resistance they are asking the specific resistance. So for specific resistance we know, if you know the R value then we can find the specific resistance easily. So then rho L by A formula, that A is nothing but this pi R square you can write, and from this they are finding this rho value here, R into pi small r square by L. So just to substitute those values, R we calculated as 10 and this pi value 22 by 7, and this small r value is nothing but it is given here 0.125 mm whole square. By this length of the wire is also given in the data here. This is the length of the wire and this is the diameter of the wire here. So this diameter is given here. So the diameter is given, they are substituting this radius here. Then on simplifying you are getting the specific resistance like this, right? So now let us see this next problem here. So see this problem. The following figure shows a meter pitch consisting of two resistors X and Y connected in parallel with a meter long constant in wire AC of uniform cross section D. Uniform cross section D is a movable contact that can slide along the wire AC. The resistors X and Y of the resistance of the segment AD and DC of the wire constitute the 4 ohms of the bridge. So they are explaining that total circuit here. So that circuit is shown in this next slide like this. This is a circuit what they are explaining here. This is the AC, X and Y, two resistors are connected here. So balancing length that they are taking it as AD. So AD and this is DC is another length here. So as we said, as we discussed here, these letters are not important. From problem to problem they may change these letters here. Just you need to remember the experimental procedure. So then the length of this AC is X 100 centimeters. X is the standard resistance of 4 ohms and Y is a coil of wire. With the Y immersed in melting ice, the null point is found to be at 40 centimeters from the point A. When the coil Y is heated to 100 centimeter, a 100 ohm resistance has to be connected in parallel with the Y in order to keep the bridge balanced at the same point. Calculate the temperature coefficient of this coil. So got it? what they are giving the data. So that means here there are two resistors or there here X and Y. So this Y is having some unknown resistance there. So now initially it is immersed in melting ice, that means at 0 degrees centigrade it is there, then we are getting this 40 ohms, 40 meters. So I think it is 40 centimeters. So change this, here it is 40 centimeters. So that means balancing length is obtained at 40 centimeters here. Now the temperature of this wire is increased to 100 degrees centigrades now. And to obtain the balancing point at the same 40 centimeters, we need to connect a resistance across this. So that resistance value is also given here, 100 ohms. So by connecting this 100 ohms in parallel with the Y, we can maintain the balancing point at the same point, even though the resistance Y is heated to 100 degrees centigrade, right? Even though it is heated to 100 degrees centigrade. And so now here, let us write our balancing length equation, balancing point equation here. So that means X by R is equal to L by 100 minus L, we can write here. Let us substitute those values here. And so now first I am taking this resistance at T degrees centigrade, we can write here. The resistance at T degrees centigrade, and when it is connected like this, at 0 degrees centigrade, once we need to write the balancing equation, and after heating that we need to write one more balancing equation here. One more balancing equation we need to write here, so that you will get this balancing, the temperature coefficient we need to consider here. So resistance at T degrees centigrade, that means 0 degrees centigrade, let us take this as R naught, the resistance of this Y. And resistance of this Y at T degrees centigrade, we are taking it as some RT, right? And so now first let us, only these two resistors are there, so let us apply our meter bits condition here. So X by Y is equal to, so this is nothing but 40 by 60 you will get, right? So then this X and Y values are given here, so that I can write this as 2 by 3. And so X is 40, X is 4 ohms is given. So 4 by Y is equal to 2 by 3 we can write. So therefore this Y is nothing but 6 ohms. And this Y only we are taking this as R naught. So that R naught value we can take it as 6 ohms. Now if R naught is 6 ohms, we need to find this in the, that means by using the first case, first set of values, we are getting the resistance of the Y at 0 degrees centigrade. And by using the second set of values, we can calculate the resistance at 100 degrees centigrade we can find here by using the second set. And by using these two values, we can calculate the temperature coefficient of this wire. So let us see here. So RT value we are taking as resistance of the wire at 100 degrees centigrade. Now here both are connected in parallel. That effective resistance I am taking it as R dash here. So that we are writing that effective resistance in the right gap. So then again we are applying the balancing equation here. Balancing point equation here, X by R dash is equal to 40 by 60. And from this again you will get R dash is equal to 6 ohms. Now this R dash is nothing but the effective of this value, 100 and Y value. And so then just to equate these two, that means let us substitute this R dash value here, so that you will get the RT value as 6.38 ohms. Now we are using just our alpha definition here, RT minus R naught by R naught into T expression we are using here. So from that you will get this alpha value. So that is the problem relating this effect of temperature on this resistance and a meter bits combination. So that means from this now you can observe that we can find the temperature coefficient of resistance also with the help of this meter bits here, right? And so now let us see one more problem based on this meter bits here. So now let us see this. It's an interesting problem. A wire AB of the meter bits changes linearly from the radius R to 2R from left end to right end. Where should be the free end of the galvanometer can be connected on the wire on the AB so that the deflection in the galvanometer is 0. So this is again our meter bits setup only, and here both are taken as 4 and 4, and so in general if the wire is of uniform cross section it should be 50 centimeters. The null point should be obtained at 50 centimeters. But here the given problem is, you can observe that this wire is of not uniform cross section. This wire is having that non-uniform cross section whose radius is changing from this one end to other end as R to 2R. Got it? The radius of this wire is it is shown in the another diagram here. The wire is actually here, it is shown as it is only, but its magnified image is shown here. That means actually the wire is, according to the given information, the wire is like this. It is of non-uniform cross section. So at one end it is given as A, at the left end it is given as A, and at the right end it is given as it is given as R, and here it is given as radius as 2R, right? And actually the resistance of this wire we already calculated when you were discussing about the resistance, right? Applications of resistance we discussed already, we calculated already this resistance of whole wire, but we didn't need that whole wire here. That means for the whole wire we mentioned that expression as like the resistance of that wire we can write as rho L by, instead of area we need to write that effective area as R1 R2. R1 is a resistance radius at one end and R2 is the radius at the other end, right? So that is a resistance of this whole wire. Now as we don't need the whole wire resistance here, we need two parts here. That means this jockey is pressed here at some point at a distance of X, then up to X one resistance, and from X to this B another resistance will be there. So like that we need to find here. So let us see that calculation here. So that means now we are taking that galvanometer is connected at the distance of X1 from this one end of this, that means from the left end we are taking here. And so that this resistance AX1 we are taking as R1, that means resistance from end of this A2 until this null deflection point here, balancing point, that we are taking as R1, and the remaining resistance we are taking as R2, and length of this wire is 100 centimeters here. And now we know the radius of this part, how to write here. We mentioned already in the different problems here. So we need to take this triangle. From the triangle you can write this radius here, right? So that means now by taking this triangle you can write this radius here. We mentioned in the different problems there. So then this value is nothing but R minus, so let's suppose this value is Rx we are taking here, Rx value, Rx minus R, and this value will get that value as R. And so that then we know already the tan theta value we can write this as in the triangle Rx minus R by, Rx minus R means this length here, this length, Rx minus R, where Rx is the radius here. This radius here, we are taking as Rx here. So this radius we are taking as Rx. So Rx minus R by X. And the same tan theta value we can write this as this opposite side. Here it is nothing but R by L. That L is nothing but actually 1 meter you can write if you are writing in terms of these meters. And so that this value we can write this as Rx is equal to R by L into X plus R. So that is nothing but what they are writing here. Rx is equal to, this value is 1 meter. So I am taking this R value common. So X plus 1 we can write here. So that is nothing but this expression here where L is equal to 1 meter I am taking here, the length. Alright, so that is expression. And we need to calculate from resistance from here to here. So first we need to write the resistance of the small element now. So let us see the resistance of the small element. So for this small element we need to write this as rho into dx by pi rx square. So this value we need to write here. And then this value we can write this expression as just this rx value we are substituting and we are integrating this value. And 0 to, we need to substitute from x value changes from 0 to some x value we need to consider here, or 0 to some x1 value we need to consider here. So that x1 limits we are substituting here. That means this value is from, limits are from this 0 to x1. This is actually we need to substitute this as x1 limits. And this actually, this limit is from x1 to L. This value is x1 to L or 1 meter you can substitute there. Then by substituting that we can find these values here. By substituting these values R1 by R2 ratio, the R1 by R2 ratio should be equal to 1 because these two values P by Q, according to the given information that P by Q ratio is equal to 1. So R by S ratio should also be equal to 1. So then we need to find the ratio of these two values and it should be equated to 1, or which is nothing but we can equate these two resistors here. That is nothing but R1 is equal to R2 we can write from this. So just you can equate those two resistors and from that you will get this x1 value here. That means the balancing length is obtained at 33.33 centimeters here. Actually, this problem you can also solve without integration here. Just for that, we know this formula here. That means if this is this wire is of non-uniform cross section having this radius R1 and R2 at the ends, then we know, we discussed already, the resistance of such a wire we can write as R is equal to rho L by, instead of area we write it as pi R1 R2, where R1 and R2 are the radius at the ends, right? Now actually, according to the given information, now we are taking this wire as a two parts here. We are keeping some balancing length somewhere here. That means this is the given wire, for example here. So here we are taking this one element here. So that means up to here we are considering, for example here. So up to here this element we are taking here. So that means this length we are taking as x1. So this length we are taking as x1 length, and this remaining length will be, you will get some 1 minus x value we can consider there, right? So this length is x1 we are taking, and this is 1 minus x we can consider here. So here radius we are taking as r1, rx, and this is r, and this radius is 2r. So then from here to here we are taking as resistance r1, this part, and this part resistance is r2, right? So that is our consideration here. This part resistance is r1 and this part resistance is r2 we are taking here, right? Now this this formula, now for this r1 we are taking this as a two separate parts. Now r1 resistance directly we can write by using this formula, rho into L. L means here x value we need, x1 value we need to write, because this is the length of this element here, rho into x1 by pi r1 r2. This end radius is r1 and this end radius is rx here, right? This end radius is rx. So then pi r into rx we need to write. And so then next similarly r2, the same formula we can apply for this. So for this end, rho into L. L means this 1 minus x1 we need to write here, and into pi r1. This is r1 r2 means here this is rx and this is 2r. So rx into 2r we need to write. So by using our Weierstrass balanced equation, then from this we can conclude that these two resistors must be same. R1 is equal to R2. So you can equate them. R1 is equal to R2. So if you are equating them, R1 is nothing but rho into x1 by pi r into x1 by rx, and this is R2 value is nothing but rho into 1 minus x1 by pi into rx into 2r. So then on simplifying this, you can cancel all these pi rx terms and rho values. Then r value, and 2 into x1. 2x1 is equal to 1 minus x1 you will get. So x1 is equal to 1 by 3, or is nothing but 33.33 centimeters you can write. That means if you know this formula, you can solve more easily this expression. That means without using this integration again, you can solve it more easily like this, right? Got it? So those are some important models based on that. And some other applications will be there, like by connecting another resistance in series and parallel across this, balancing length shifts by balancing point shifts by 2 centimeters or 5 centimeters, such a problems will be there. So it's just they will give it as shifts by 5 centimeters, for example, if it is given. Whether it is shifting to right or left, that you should decide according to the given problem. For example, here we are connecting a small resistance in parallel with it. Then balancing length shifts is 5 centimeters means how it shifts. That means now here it shifts this side here, because here whenever you are connecting a resistance in parallel, whether you are connecting a small resistance or high resistance, the effective resistance will decrease, right? That we know already. So when effective resistance decreases means here this balancing length also should decrease here. Then that shift we need to take it as 5 centimeters this side we need to take. And so then if it is a uniform wire, then you should get it 50 centimeters for example. Then here now we should take it as 45 centimeters as a balancing length if it is a uniform wire. So like that we need to take here. If you are connecting another resistance in series with this, another resistance series, some R ohms is connected here. As the resistance in this gap is increasing, the balancing length should increase here. So that this shift we need to consider this side. So such a type of more problems will be there based on this. And so then solve all those problems based on this. So it is a meter bridge experiment and meter bridge device and working experimental setup. We discussed experimental setups and what are the precautions to be taken while using that experiment. In errors only we discussed that current should not be loaded for a long time and jockey should be pressed at different points, but it should not be dragged along those. Those are nothing but we can mention them as precautions. And we discussed some important models based on that, right? So then practice the remaining problems based on this meter bridge. So in our next class we will discuss about the another device will be there. So about the device we will discuss that in our next class, meter bridge, potentiometer. And before that, we need to discuss about some rheostat also. I will explain that about the rheostat also in our next class. Thank you. Practice problems based on this meter bridge now today.